Hi and Assalamualaikum. In this video, we will present an explanation of Chapter 2, which is about resultant forces in equilibrium. In everyday life, objects like ladders, loads on strings, or objects on slopes may remain at rest even though forces are acting on them. This happens because the forces are balanced. In physics, this is explained using the concept of resultant force. The objective of this topic is to understand that an object stays at rest when the forces acting on it are balanced.
My name is Nur Amanina Akhalili. The resultant force is obtained by combining all the forces acting on an object into one net force. An object is considered to be in equilibrium when the net force acting on it is zero. So, meaning that there is no acceleration occur. The objective is to define the concept of resultant force acting on an object.
My name is Farhana Alia. My student ID is 2024231592. So, for some equilibrium cases that involve three forces acting at a point, we just apply Lami's theorem, which is Lami's theorem helps us to relate the force using angles between them. So, this can connect with our objective, which is students able to apply Lami's theorem to analyze system involving three concurrent forces.
My name is Megat Shakir Zufairi bin Zainul Abidin and my student number is 2024963235. For complete equilibrium, not only the forces must balance, but the sum of torques must also be zero. In this presentation, we will apply these ideas to inclined planes, string systems, ladders, and torque. The objective is to solve basic equilibrium problems using force and torque principles.
Okay, so now I will continue with my part, which is what is an inclined plane. Inclined plane is a flat surface still at an angle. It makes work easier by less the effort needed to move a load. Inclined planes are often used for moving heavy loads over vertical distance. Okay, so instead of lifting something straight up, you push or pull it along the slope. So why does it help? It doesn't make the object lighter, but it expands the weight over a longer distance. This means less force is needed at once, so you can move heavy things without needing super effort. Okay, so you can see here, the longer the ramp, so the easier it is to push something out. But you will walk a long path. If you choose the longer one, it will feel much easier even though it takes more time. Okay, so when an object is placed on an inclined plane, there are main forces acting on it. First is weight. So the weight is always acting vertically downward, and the friction acting along the plane if the surface is zero, and the direction acting perpendicular. Okay, then now we move to the simple question about the inclined plane. Okay, so block of weight 60 Newton rests on a smooth plane inclined at 30 degrees to the horizontal. So find the normal direction acting on the block. For the first, we need to draw it first to make it more clear. Then we need to label all the forces that acting on it. Like here is W wave and the normal direction. And after it, we need to assume the x-axis and y-axis at the inclined plane, and we need to label all the forces that acting on it. And after it, we need to transfer into the table and label the forces, x-axis, and y-axis. Then we need to list down all the forces that acting on the inclined plane. And then if you can see here, for the y-axis there is a number, and then for the W at the x-axis there is a negative 60 sine 30, and y-axis is negative 60 cosine 30. So then we need to sum up all the x-axis and y-axis. Okay, but for this question, we just need to find the normal. So we need to sum up for the y-axis only. Which is, we will get the normal reaction is 51.96 Newton. Okay, so for the next question, a block of mass 5 kg rests on a plane inclined at 25 degrees to the horizontal. So the coefficient of friction between the block and the plane is 0.4, and the value of G is 9.8 meter per second square. The question asks us to find the frictional force acting on the block. So first, we need to list down all the information in that question, which is here is M is equal to 5 kg, coefficient is equal to 0.4, G is equal to 9.8 meter per second square. And then we need to label all the forces that acting on the plane. So because it is a plane, so there is a friction. So after we need to assume the x-axis and y-axis at the inclined plane and label all the forces, which is with normal and the friction. And then we need to transfer into the table like before this, forces, x-axis, and also y-axis. And then we need to list down all the forces into the table, as we know that the formula for the weight is W equal to mg. So for the M is 5 and the G is 9.8, and we will get the 49 Newton for the weight. And then we need to list down all the forces into the table. And if you can see here, for the y-axis there is a normal, and for the x-axis there is a friction, and for the W at the x-axis there is negative 49 sine 25, and y-axis negative 49 cos 25. So because there is two unknown, so we need to sum up all the x-axis and y-axis. Then for the friction, we will get the 20.71 Newton. The y-axis, we will get the normal, (44.4 Newton). And then the question is to find the frictional force. So formula for the frictional is equal to mu r, and the mu is 0.4 and r is 44.4, and we will get the 17.76 Newton.
So hi everyone, I will continue with resultant force, which is string in equilibrium. So we'll go straight to string scenario 1. So from the photo, how many force acting on the hanging lights? So as you guys can see, there is two string attached to the light. So that means when there is a string, there will be one force acting throughout the string, which is tension. So for these things, we will label the tension as TLP because there is two string acting on it. So it is easier for us to label the string. So T is tension, which is tension will acting along the string, pulling away the object. So in this scenario, the string will pulling the lights. So for another string, there will be also one tension acting upward, which is, we label this as TLQ, and it will acting along the string LQ. So there is also one more force acting on it, which is weight. Weight is equal to mg, which is mass times gravitational acceleration. So we have to always remember that weight is always acting vertically downwards. So there is 3 force acting on this light. So resultant force is vector sum of all force. So in this scenario, it is in equilibrium, so the resultant force will equal to 0. We'll move to example question. So let we read the question and do the what force acting on the photo. So the diagram shows 2 bottles A and B of mass 0.3 kg and 0.25 kg. So they will given a mass, so we can find the weight. Weight is always acting downward. So for A, the weight is 2.94 Newton, and for B, weight is equal to 2.45 Newton. We can already count it. So the particles are suspended below a horizontal shielding by 2 strings AP and BQ. So there also, we already know there is a tension AP, TAP and TBQ attached to fixed point P and Q on the shielding. So the bottle are connected by a horizontal string AB. So there is also one string connected A and B. So of course, when there is a string, there will be a tension. So tension AB from A and tension AB goes from B. For angle APQ is 60 degree and BQP is theta, so unknown. So each string is light and extensible. The bottles are in equilibrium. So we have to find the value of tension in the string AB and theta and the tension in the string BQ. So let's find out A first. I will give example. If I take it from B, I will do the free body diagram. So TBQ, we just sketch back what we already have done from the photo on the left. So as you guys can see here, there is no other information, so we lack of information here. So we try to do the free body diagram on A because I think we can do something with the 60 degree. So there will be TAP and then TAB going to the right and weight. So as you guys can see, there is 60 degree there, so we can do something and we can put a parallel line here, so there will be also 60 degree there. And then from that, we already know there is 90 degree between TAP and the weight, and also 90 degree between TAP and the weight. From here, we can actually find the angle here, which is when there is 2 parallel line, the total angle in the shape is 180. So 180 minus 60 is equal to 120. So by doing this, we can already find the tension AB by using Lami's theorem. So which I just put TAB over sine 90 plus 60 equals to TAP over sine 90, and weight we already have find 2.94 over sine 120. So because we want to find TAB, so we just take TAB over sine 90 plus 60 equals to the one that already full with information. So we just take the TAB on the left and the other one, just take it to the right and we'll multiply it. And so we will get TAB is equals to 1.6974 Newton. So we will move to question B, which is find the value of theta and the tension of the string BQ. So we just take the free body diagram that we have from A. So now, by doing this, we can take the theta and put a parallel line here. So we can using Lami's theorem. So we take 2.45 over sine 180 minus 60 minus theta, because we want the angle between TBQ and TAB. So 1.6974 over, which is tension AB, over sine 90 plus the theta, because we want the angle between TBQ and the weight, and equals to TBQ over sine 90. So actually we have to do a simultaneous equation because there is 2 unknown things in this Lami's theorem equation. So we just have to TBQ sine 90. We take it 90 to the right, and that will be our first equation. And TBQ equals to 2.45 sine 180 minus sine theta times the sine 90, which is we take it from the left to right. So that will be our second equation. So as you guys can see, TBQ, we already have two equations, which is TBQ is equals to what, and the unknown part is theta. So we can take one equation first is equals to equation 2. So we just take it from there and cross multiply it. So we will get, so we just have to multiply left to the right, and we will get, and we take all the sign to the left and all the number to the right. So we will take out the sine theta, and so that we will get numbers. So the negative 6974 minus 2.45, we will take it to the right over the 2.45, and then sine theta, sine we will take it to the, we will bring to sine to the right, and it will be sine inverse. So theta is negative 36.488. Why it is negative? Because the angle of the theta is below the x-axis. So now we can find this tension in the string BQ, which is 2.45. We just fill in the theta, unknown theta, because we already calculate the theta. So TBQ will be 4.12 Newton. So I hope that you guys really enjoy this. I hope that you guys can understand this really well.
Hello everyone, my name is Alia. I will talk about resulting forces in ladder. As you know, ladders are used in many real-life situations, whether it's leaning against a wall or someone climbing up. Even though the ladder looks still, there are actually many forces acting on it at the same time. Now, let's look at the forces acting on the ladder. First, we have the gravitational force W. This force acts downward at the center of the ladder due to the weight of the ladder itself. Next, at the ground, there is normal reaction force. I label it as R1. This force acts perpendicular to the ground surface. At the same point on the ground, there is also a frictional force Fr. Friction acts opposite to the direction of motion. Finally, at the wall, there is another normal reaction force labeled as R2. This force acts perpendicular to the wall. We move to the real-life example. A firefighter used a uniform ladder of length 6 meters to reach a window. The ladder rests on a rough horizontal ground and leans against a smooth vertical wall, making an angle of 70 degrees with the ground. The ladder weighs 300 Newton. A firefighter of weight 700 Newton stands 2 meters from the bottom of the ladder. The question is to draw a clearly labeled free body diagram showing all the forces acting on the ladder. So, the forces acting on the ladder are W1, the weight of the ladder, which is 300 Newton acting vertically downward at the center. W2, the weight of the firefighter, which is 700 Newton acting downward at 2 meters from the base. Next, we have R1, the reaction force from the smooth vertical wall acting horizontally. Another R, which is R2, the normal reaction force from the ground acting vertically upward. And the last one is Fr, the frictional force at the ground. This diagram helps us to identify all the forces clearly before solving the problem. Next question is to determine the normal reaction force at the ground. For this question, we apply the condition for vertical equilibrium. Since the ladder is at rest, the total upward force must equal to the total downward force. So we write R2 minus W1 minus W2 equal to 0. And then we substitute the values of W1 and W2. R2 minus 300 minus 700 equal to 0. R2 minus 1000 equal to 0. And the value of R2 is 1000 Newton. Therefore, the normal reaction force at the ground is 1000 Newton. And for question C, calculate the reaction force exerted by the wall on the ladder. Now, we calculate the reaction force exerted by the wall, which is R1. We take moments about the base ladder to eliminate the forces acting at the point. So, we take moment for W1, W2 and R1. For W1 equal to 300 sin 70 degrees times 3, W2 700 sin 70 degrees times 2, and for R1, R1 sin 70 degrees times 6. So clockwise moments must equal to anti-clockwise moments. So we write R1 minus W1 minus W2 equal to 0. We move the W1 and W2 to the right, so R1 equal to W1 plus W2, and substitute the values. R1 sin 70 degrees times 6 equal to 300 sin 70 degrees times 3 plus 700 sin 70 degrees times 2. So we get 5.6382 times R1 equal to 2161.293. R1 2161.293 over 5.6382, and we get R1 is 383.33 Newton. Okay. The last part is we look at the sample exam question. The question is, a 4 meter long uniform ladder weight 200 Newton rests against a smooth vertical wall. The ladder makes an angle of 60 degrees with the rough horizontal ground. The ladder is in equilibrium. Question A. Draw a free body diagram of the ladder. So the force acting on the ladder are R1, the horizontal direction force from the smooth vertical wall. R2, the normal direction force from the rough horizontal ground. And then we have W, the weight of the ladder, which is 200 Newton, acting vertically downward at the center of the ladder. Last one is Fr, the frictional force acting at the base of the ladder. So we move to the question B. Using the free body diagram drawn in question A, calculate the horizontal direction force exerted by the wall on the ladder. To do this, we take moments about the base of the ladder, which is moments for R1 and moments for 200 Newton. So for R1 times sin 60 degrees times 4, and for 200 Newtons, 200 times cos 60 degrees times 2. We make it as equation 1 and equation 2. Since the ladder is in equilibrium, clockwise moments must be equal to anti-clockwise moments. So we write equation 1 equal to equation 2, and we simplify it and get 4R1 times sin 60 degrees equal to 200. We bring the sin 60 degrees to the right and get 4R1 equal to 230.9401. Bring 4 to the right, we get R1 equal to 230.9401 per 4, and get R1 equal to 57.74 Newton. And we move to the last question, is to determine the direction force exerted by the ground on the ladder. We use vertical equilibrium, and upward forces must equal to downward forces. So R2 equal to W, and the value of the W is 200 Newtons. So the value of R2 equal to 200 Newton. And the last one is the frictional force acting at the base on the ladder. We use horizontal equilibrium. R1 minus Fr equal to 0. Fr equal to R1, and the value of R1 is 57.74 Newton, and that's the value of Fr.
What is torque? Torque is the ability of a force to cause an object to rotate. The greater the force or the longer the distance from the pivot, the larger the torque. Imagine yourself in the playground, going to push a merry-go-round. It rotates faster as you push it, but it takes more work to push when you're close to the center of the merry-go-round than when you are pushing at the edge of it. This difference results from a phenomenon known as torque, which describes the rotating force exerted on an object. When you push or pull an object in a straight line, you exert a force on it, while torque is when you exerted force on a rotational object. Torque is a vector quantity, meaning that it has both magnitude and direction. Mathematically, the magnitude of torque can be represented by this formula. Torque is equal to F times D, which F is magnitude of force measured in Newton, and D is represent the perpendicular distance from the axis of rotation, measured in meter. So the SI unit for torque is Newton meter. The right hand rule can determine the direction of torque. Point the fingers of your right hand in direction of the applied force, then curl your fingers in the direction of the object rotates. Your thumb will show the direction of the torque. If the thumb points out of object, the torque is anti-clockwise. This will give positive torque, but if the thumb points into object, the torque is clockwise, give negative torque. In many common conditions, torque is observable. You may have noticed that door handles are always positioned far from the hinges, which act as the door's axis of rotation at the door's edge. Because of this design, pushing or pulling a door requires less force because a larger distance from the axis of rotation produces more torque. It takes a lot of force to generate enough torque while trying to open a door close to its hinge. Considering a nut and a wrench, if the nut is locked up, it is very difficult to unscrew it with a small wrench. It will be a lot simpler if you use a long wrench. Torque is the reason behind that. Applying 90 newtons of power with a 30 cm wrench results in 0.3 meters multiplied by 90 newtons, which will produce 27 newtons meter of torque. On the other hand, if you apply the same 90 newtons of force to a wrench that was 60 centimeters long, so we take 0.6 meters multiplied by 90 newtons, which will result in 54 newtons meter of torque. Therefore, you can see from this straightforward maths that using a longer wrench applies greater force to the nut. Let's take a look at the piston in engine. Torque values can provide better acceleration with larger piston, which is advantageous for automobile engines. Next, torque also play a crucial role in sports, especially those involving a lot of swinging motion, such as baseball or cricket. In baseball, batters usually hold the bat as far away as possible from the expected point of contact with the ball and generate significant force when swinging the bat. This action maximizes the torque at the point of contact, allowing the ball to travel a long distance. Let's take a look on an example. Forces are applied on the beam as shown on the figure at the right. A. Find the torque about point P produced by each of the three forces. B. Find the net torque about point P. C. A fourth force is applied to the beam at a distance of 0.3 meter to the right of point P. What must the magnitude and the direction of the force be to make the beam in rotational equilibrium? Let's start with question A. It is easier of listing out each forces and perpendicular distance in the table so that we can find each torque. The first torque, which is 20 newtons times 0.15 meter, will produce negative 3 newton meters of torque in clockwise direction. Second, 50 newtons times 0.25 meter will have 3.75 newton meter of torque anti-clockwise direction. And lastly, 5 newtons times 0.35 meter will make negative 1.75 newton meters of torque clockwise. For question B, the net torque is the summation of all torque exerted. Gather all the torque, thus the net torque is negative 1 Newton meter clockwise. This means that the beam is rotated about 1 Newton meter of torque in clockwise direction. The last question told us that we have new force applied on the beam to ensure it is equilibrium. To calculate the rotational equilibrium, the clockwise and the anti-clockwise magnitude of torque must be the same. Just now, we knew that the beam is rotating in clockwise direction, so the additional force must be in the anti-clockwise to keep it equilibrium. Now we have 3 at 1.75 equal to 3.75 plus the fourth force times 0.3. Then calculated the fourth force and we get 3.33 Newton anti-clockwise direction. In conclusion, torque is the turning effect of force. It depends on the size of the force, the distance from pivot, and the direction of the force. Torque plays an important role in many everyday activities such as opening doors, using tools, and driving a car.